I've already secured my place in history, not necessarily through this talk, we'll see, but through this picture. And I just checked the date. It's kind of scary to say, but this was actually 2003. I just found the email. I just looked it up in Buenos Aires, and the historical significance of this picture of Yuri that I took there in some walk in some suburb of Buenos Aires is that Zoya, his wife, at some point said, "This is the best photo I have of Yuri." So I want him to use it for his webpage or something, with a kind of assurance that you would expect from her, and which leaves no room for a discussion or dissent. So I don't know if she's still using it, but this is my great pride, Yuri, Buenos Aires, 2003. So when is this thing not working? It was working like 30 seconds ago. The work that I'm going to present is indeed called Programming Really is Simple Mathematics. Maybe I should say, since lots of people have asked me about this strange name, Constructor of Technology, very quickly, it's a new institution, higher education institution located in Schaffhausen in Switzerland, the place of the famous Rhine Falls, the biggest waterfalls in Europe. And we are new, we are small, we have 3 chairs. Focused on software engineering and quantum computing, with 2 associated chairs at the University of Geneva in quantum technologies. I'm one of the professors there. We have about 12 PhD students, and we also have 2 master programs, including one which combines software engineering topics with management topics, the kind of thing that we find more in MBA. So as I said, we're still very small, and you're welcome to ask Reto or myself if you want more details. So the history of this work is that it's actually something that I worked on and off between 15 years ago and 10 years ago. Then I kind of I published a paper, and I kind of put it aside, and then I gave a presentation to my group at Constructor some months ago, and Reto got interested in it, but he wanted to do something more rigorous. So in particular, he started trying to prove all the properties that I had ascertained in my great self-assurance, and which, of course, in some cases were right, and some cases were not. So we have continued working on this, again, kind of on and off since then, expanding the theory, and I'm going to try to present where we have. The other remarkable thing about Reto is that he took my introductory programming class at ETH a number of years ago in German, and he survived it and still talks. He still wants to do a PhD with me, which is, I mean, it means he's a quite remarkable man already just for that. So why is this thing not working? This is kind of, okay, no, it was working like 2 minutes ago. So the thesis of this work is that we can understand programming in terms of elementary set theoretical concepts. And when I say elementary, I mean elementary in the sense of elementary set theory, the kind of things people learn at the age of 15 or so, nothing deep. And I think it will make our understanding of programming better if we can indeed do this. So that's why we call it Programming Really is Simple Mathematics. Now this slide is a lie in the sense that the real purpose of this talk is to secure an invitation to EuryFest 19. Okay? So I will see in the end if we have succeeded or not. So the features of the theory to advertise for it are the following. There are no axioms. There are definitions, but we don't need to introduce any axioms above those of normal set theory, Zermelo, Frankel, or it doesn't really matter what the basis is. A single concept covers specifications and programs, so we're not going to distinguish between specifications and programs. It's a relative distinction rather than an absolute one. Everything proceeds from 3 basic operations. We also define refinement as essentially subset. It's not quite as simple as we would like it to be, but it's very close to being just subset. We are able to derive the laws of some classic papers that I'm going to cite in a couple of minutes, which are typically asserted as axioms. We are able to derive them as theorems, which I believe is always a good sign. So we have actually dozens of theorems which are all mechanically verified. We've been using Isabelle HOL. It could have been used. It has actually turned out to be a good substrate for what we do, and everything is available in a public repository. So I'm going to start by criticizing other people, and of course I'm kind of shooting high, so I don't think that the reputations of Bob Floyd and Tony Hoare and Gilles Kahn are going to suffer much from a little criticism from me, and of course it's all criticism for a good cause, right? To recognize the insight of these pioneers and to see how we can go further. So the field of semantics of programming languages and programming verification started in the 60s and 70s with a few seminal papers, such as this one by Bob Floyd, which was then refined by, the approach was then refined by Tony Hoare in giving the axiomatic method of specifying programs and programming languages. And the paper was famously titled Assigning Meanings to Programs. So you take programs as an object, right? As objects, like objects from the natural world, like birds or stones or electrons, and you try to talk about them. Okay? And now, Abrial famously, I think just as famously, reversed this perspective by saying we should actually be assigning programs to meanings. This was very clever, and I think it's the right starting point. That is to say, it's not that we have programs and you try to figure out what they are. It's actually that we build programs as representations of some meaning. So we're trying to go one step further, which is Abrial, who, by the way, passed away like 2 weeks ago. Do you know? Remember, we actually, shortly after that, we had dinner with him. Yeah. And so and we're going to go, I think, one step further by basically not distinguishing from meanings and programs. We're just going to, between meanings and programs, we're just going to look at meanings, you know, the kind of things that we want to do with a computer. So let me explain what we are reacting against. There's a very famous paper by Hoare and a whole group of people describing the laws of programming, and it has things that really shocked me the first time and the second time and the thousandth time I looked at it. Things like this, you know, P union Q is equal to Q union P, except that it's not union. Okay, it looks like union, it smells like union, it walks like union, it sings like union, but it's actually choice. Okay, and then surprise, surprise, it's commutative, it's associative, it's idempotent, and well, so okay. If it's, I mean, couldn't this be union? I mean, the very, very naive question, right? And then there's actually something really, in my opinion, deeply flawed in this approach. So he cites. Hoare cites Bertrand Russell, I mean, who at least has the right first name, right? But other than that, actually, I'm a great admirer of Bertrand Russell. He's my cousin, right? He was the Lord. He's okay. Anyway, so actually, the citation of Bertrand Russell, I've only found it in text by Tony Hoare citing him. So I don't know if it's really genuine. But Russell is supposed to have said. That the axiomatic method, that is to say you postulate what you want, has the advantages of theft over uninstall. So when you're a lord, okay, and have servants to help you, it is said that Bertrand Russell, I'm getting personal here, never actually learned how to cook eggs, to cook hard-boiled eggs. So sure, it's easy to joke about theft being better than uninstall, but it's not true. It's just not true. I mean, normally we promote uninstall over theft, and of course you can postulate everything that you that you want. But sorry, since I don't have my pointer, it's not so easy. Yeah, I mean, it's very easy to postulate things, but how do you know that what you've postulated makes sense, so that it's consistent, for example? And it seems to me that actually I mean, not being a mathematician myself, my understanding of mathematics is that you actually do the reverse. You try to start from as few axioms as possible, and then you prove everything else. And I think we have kind of moved away from that in computer science. If you look at formal methods, there's lots of formal methods papers. There's lots and lots of axioms, and they don't prove that much. So we're trying to do the reverse. We're trying to be axiom poor and theorem rich. So here's another example, and then I promise I'll stop bashing at all the great computer scientists of the world, and I'll give you an opportunity to bash me, to lash at me instead. So this is another great computer scientist, and he had Gilles Kahn, and he had this seminal paper in the 70s, natural semantics, I'm sorry, 80s, no, it's not, 87. And so he defines the semantics of a simple programming language, and it has things like this. I've highlighted one because otherwise it's too small. So this is the semantics of the if then else, right? If then E2 else E3. So what is an if then else? Well, you need to have this notion of binding. So rho is a binding, and this kind of notation here means that under the binding rho, a binding, of course, is a mapping between variables and values. And this kind of notation says that if it says that under the binding rho, E1 evaluates to false. So what it's telling us is that in order to know the semantics of this expression, I said a conditional instruction is actually a conditional expression. In order to understand the semantics of this conditional expression, you need two cases. I'm only showing one. And if it is the case that under the binding rho, E1 evaluates to false, and also under that same binding rho, E2 evaluates to alpha, then under that same binding rho, this expression here will evaluate to alpha, and then in the other case it will evaluate to the other thing. Okay, do we really need all this machinery to understand when you're like I did yesterday, when you are driving from Zurich to Munich? At some point there is a sign which says, you know, go left for Stuttgart, go right for Munich, and I think most of us logicians or not, program semanticists or not, can understand this without having understood, for example, the notion of binding. Or it would seem that if we really want to model this mathematically, and basically this is what we're going to do, we're going to say we have a set, and there are two subsets which we can call C and not C actually. It's better to call it C prime, the complement. And on C we do A, on the C prime we do B. This is the kind of thing that we should be using to model such notions without resorting to this whole apparatus of complicated concepts. So that's what we're trying to do. Okay, so how are we doing it? The basic idea is here. We call program or specification the following. It's a combination of a relation and a set. So we have a set of states, which we call S, and we have the program is basically a relation. So I'm using this notation here to indicate, so it's the same thing as is the power set of S, the Cartesian product of S and S, a set of pairs. One relation is a set of pairs, and the set of relations is the set of such pairs, such sets of pairs. So we have a relation which we call the postcondition between states and states, and a precondition. So first, the relation, it simply indicates the relation between, in the ordinary sense of the word relation, between the initial state of the computation and the final state. So this is somewhat limiting in the sense that it doesn't take into account like continuously operating programs, things like this. For the moment, we're just focusing on input to output programs. It's probably not too difficult to generalize, but one has to start somewhere. So that's the post-condition. And then life being more complicated than we would like it to be sometimes, we also have to take into account a precondition, which is the subset of the set of states under which we expect the program to operate correctly. Okay? So we call this the precondition. So that's it. It's both a program and a specification. So to me, this is an important concept, an important idea, the idea that there's no fundamental difference between a program and a specification. It's just a matter of a level of abstraction. If I take something which to many people would appear as a program, like an assignment, X receives 5, it's an implementation, right? It's a program. Well, if you're a compiler writer, it's actually a specification for something probably pretty complicated. So this relationship between the notion of, this difference between the notion of program and specification is a relative difference. We can say that a certain program / specification is an implementation of another, which is more abstract, but that's what it is. This is the only difference, and we can use the terms program and specification interchangeably for the rest of the discussion. I'll just say program. So that's the basis. Then we have a few, notations. So if we have such a program, we can write it as a pair like this. Because the post condition is the most important part, we put it first. It's kind of counterintuitive, since pre comes before post, but it's actually more convenient to put the post condition first. It's just a convention. Now, my hidden agenda, which is not so hidden since I'm mentioning it here and everywhere, is to reconstruct a programming language, namely IFO. Okay? So the idea is that we're going to have a mathematical theory, and then we put notation on top of it, syntax, but we start from the semantics, which is what I'm doing here. And then as we go, we put on some syntax, and surprise, surprise, 1 year from now, you will have the complete construction, which looks exactly like IFO because it is IFO. Okay? So that's all that I'm trying to do, but don't tell anyone, especially not him. So here are some basic programs. Again, it's all pairs of the post and pre condition. So fail is it's the same thing as Dijkstra's abort. It cannot do it. It accepts nothing, and in any case, it could not produce any result. Okay? Infeasible, it accepts everything, but never produces anything. Havoc, it accepts anything and produces anything. Univ is the universal relation, which holds between elements of any pair, between the first and second element of any pair. So it's havoc. You don't know, you have no idea what it's going to produce. Skip.
Or is this the pre on the left side?
It's the post. The post is first, and the pre is a second. So univ is a relation. So skip, it accepts anything but doesn't. So ID is, as you could guess, the identity relation. Right? It doesn't change the state. And then skip it would. There's also skip. This is not so important. It's useful technically in some proofs, but we can also restrict skip. That's what it does. Skip underscore under skip sub C is skip restricted to a certain subset. I don't understand. So C is a subset, but it's the same thing. A condition is a subset of the set of states. So one can go with logic or set theory, and as a matter of taste, we find it more convenient to use subsets. So a few notations just to I'm trying to restrict the notational overload of this talk as much as possible, but I think it's useful to introduce those notations. So we can restrict a relation to a subset of its source set, so that's slash. we can co-restrict it to a subset of its range or of its target set. For composition, being a programmer, I don't really like this standard mathematical notation because I think I have to go maybe to predict the past or something like this. So it's just the same thing. It's composition of relations, but in the order in which they are applied in the order in which they are given. And then we use these two notations here for the domain of a relation and the range of a relation, underline and overline. Okay. So so programs have, as I define them, a very general definition. So now we're going to restrict programs so that they're kind of tractable in a very naive sense of the word, tractable. And so in particular, a program is or is not feasible. Feasible means that the precondition is me. It's the denotation semantic people taking their revenge.
That's right. I mean,
Remotely, can you still see my slide or not?
Yeah, on
can.
Zoom they can see, but the problem is here we cannot see anything.
We can see the slides and we can hear you, but the sound is very weak as usually.
The sound is very weak. Even though we raise to the maximum.
No, okay. When you speak directly in the microphone, it's more or less okay.
Okay.
I'll do my best.
So here you can hear?
Yeah, that's very good.
Now much better.
Now much better. Okay, so you have to get the microphone like this. It's difficult, but
I'll try to put it.
No, wait.
Yeah, it's not going to hold. No.
Let me see. Here it is.
1 second.
So how is it?
Can you close this?
I need to shed a few pounds. No, but okay. The other thing is, sorry. I had a tie.
That's supposed to be wireless. But
the beamer goes wireless to here somehow.
yeah,
The beamer is connected to
let's restart the beamer as well and see what happens there.
The connection from there to them is wireless. So we can try, I have a cable.
Yeah.
Again, try the situation with the point with the cable, but I don't know if
I think that now it cannot be because I mean we have other, like I don't know. Let's restart that, and the other cable didn't. The other adapter didn't really work. So let's restart it. Exactly. So, but on Zoom you can still hear us, right?
If you do like this, it's wonderful.
Yeah. When we speak like this, then you can hear Stefan.
Excellent. It's really good.
Perfect.
Yes, we can hear you, yeah.
Yeah. 1 second.
And the other one doesn't work.
Restart that.
The other beamer doesn't work. Which you had problems.
worked yesterday without any problem. So
yeah.
Can try the other thing.
That's gonna be
days on and days off.
Yeah, that's gonna be.
It's
very Catholic.
It's a unionized.
The beamer is very Catholic. So take a break.
Yeah. He waits.
I'll get myself some water in the meantime. So why in the meantime, why is this thing not working? Yeah.
Yeah, that works. Okay.
Is it going to be okay for them?
Yeah, yeah.
Oh,
But then they will continue seeing what you're sharing.
And now this thing is working. Miracles.
Yeah, yeah, that's.
I just changed the USB port. Okay. So we programs may have or not have certain reasonableness properties, which we call feasibility and roundness. The word roundness is debatable, but feasibility, I think, is clear. So we said that a program is feasible if its precondition is a subset or equal to the domain of its postcondition. Okay? So this audience doesn't need pictures, but there's a picture anyway. You can see here that we have an unfeasible program because there's this element of the precondition, this red dot, which is not in the domain of the postcondition. So if we look at it from the viewpoint of a programmer, it means that we have an input that satisfies the precondition, but for which the program isn't able to do anything. So it's a bug, right? It's like, for example, you have a domain which, say you're trying to compute a real square root, and the precondition has not been made strict enough to exclude negative numbers. So if that's the case, we said that the program is infeasible. Precondition is not a subset of the postcondition.
Suppose you go from one domain to a completely different domain. You start from strings and go to natural numbers. Then on the right, you have natural numbers, maybe all of them.
Yeah, but we have functions from states to states. These are state transitions. Mm. So we don't go from one domain to within the state, we might have we might have the input part of the state and the output part of the state. But okay. This is all.
Sorry.
Yeah. So in more informal terms, it's a buggy program because there are some inputs that it's not going to be able to process. And the other way around, let's assume that we have an element of the precondition that is not in the domain of the postcondition. So you could say this is less bad, but it's a problem anyway because we can call it dead code. You know, here, for example, we have elements that do not satisfy the precondition, and the relation is still defined for them. So it's not necessarily a catastrophe, but in programmers' terms, it corresponds to dead code. Okay, code that is the precondition is broad enough, so it says you can handle. So, no, sorry, the precondition is restrictive, it's the other way around. It says it cannot handle such cases, but in fact, the program could. And if a program is both feasible and rounded, then we say it's exact. Okay? So now we have a few notations. If we remove the dead code, we write it like this. I hope it's readable on the screen. It's a bit small, with the kind of an upper symbol. If it's so, this is the feasible version. It's the version where we have removed from the precondition anything that it is not in the domain of the postcondition. So that's the rounded, the feasible version of a program. If there was a verb, I would call it the feasible, okay? The version made feasible. Then if we round it, it's the other way around. If we restrict the postcondition to its domain, to the domain intersected with the precondition, then we round it, and then it's the exact version, and then we start pushing the button, and I'm sorry, I shouldn't call you a button. So we start having some properties. They are pretty elementary at this point. Okay, then a basic notion of refinement. So it corresponds to the intuition that refinement is subset. So basically, refinement means that the postcondition of the refined version is a subset of the postcondition of the original. Remember that these are relations, right? So it's subset in the sense of a subset between relations. Each pair of the left-hand side is also a pair on the right-hand side. So it would be nice to have a single definition to say, for example, that a precondition can only be increased, weakened, or that it can only be strengthened, restricted. Unfortunately, what we found is that depending on the cases, we need one or the other. So there are two relations which we respectively call specialization and refinement. And if we accept strengthening the precondition, it's refinement. That's right? And if we the other way around, it's specialization. So it's almost the same relation, refinement and specialization, but some properties are the same, some properties are different. And then we say that Q implements P if it refines it and is feasible. So an implementation of a specification is a refinement of it, which is feasible. And again, there's no difference of nature between P and Q. They're both specifications/programs, but one provides a feasible representation of the other. Now we introduce some basic operations on programs. They're not yet programming language constructs. They're pretty close, but the actual programming language constructs will be based on them and come in a few minutes. So the three fundamental operations are here: restriction, choice, and composition. And they're very much the corresponding set theoretical, elementary set theoretical operations. So looking only at the postcondition in the interest of time, restriction is just a different notation, which is kind of stolen from Dijkstra in the guided command style. So this is the program that is obtained by restricting the input domain to C, basically. And there's something, I'm going to skip the precondition part. Then we have a choice, non-deterministic choice, which is the union. That's really what we wanted to have. So unfortunately, it's a bit, what I would really like to have here is post sub P union post sub Q, but we actually, in order to avoid some unpleasant, unintended consequences, we need to round it in order to have something that is meaningful. Otherwise, basically, if you try to do it, you will see that if we take just the union of the postconditions, then it can introduce some spurious elements which are neither in the original one nor in the other one. So we need to take the rounding. And so this basically, this is, if you like, a limited, just to, yeah.
To do this, do P and Q have the same P conditions then, or can they differ? So can you, the point is, this is non-deterministic. If the left-hand side is, if the left-hand side is, let's say, undefined and the right-hand side is defined, then you choose the right-hand side. So is this angelic, or do you require, I don't understand it from this notation, or do you require that in order that non-determinism works, both sides have to be defined? For example, I mean, this is...
Well.
We have this
yeah,
demonic,
so the
angelic,
question- so-
different kinds of
so-
non-determinism.
So ideally, it should be, because, you know, the basic concern is the simplicity. Ideally, here it should say post P union post Q, and here it should say P union pre-Q. So
Okay.
if you do this, then you end up with paradoxes. So you can either restrict the precondition, that's the
Yeah.
other approach, or you can restrict in an informal sense,
Mhm.
or restrict the postcondition. And then there are no, so whether it's angelic or demonic non-determinism, depending on the exact meaning.
Let's discuss it.
I have to think
Yeah.
to give you a correct answer, because we have to define angelic and demonic precisely. So yeah, this is where, you know, my grandiose statement that it's just basic elementary set theoretical operations kind of hits a wall, because it's not quite as simple as we would like it to be. It's essentially true, but there are some technical restrictions that we have not been able to remove. And then composition, same thing. You can see that we have to round the second element. So I would like it to, so you have to understand that this, maybe I should use a different color or something, but you know, this is an operator on programs defined in terms of an operator on relations. And that is the goal, to say the operation on program is just an operation on relations. Unfortunately, it's not quite as simple as that. Still, essentially, it is, I mean, the composition of programs, you sequence do A, then do B, then do C, the semicolon of programmers. Fundamentally, it is composition of relations, but the technical details are not quite as simple as we would like them to be. So here come another set of properties. So these are all theorems. You know, you don't need to assert these things. You don't need to take them as fundamental laws. We just prove them, and again, they've all been proved mechanically. So it's what you would expect: commutativity, associativity, and so on, and more for computation. And yeah, it seems like just to pick one more or less at random, if you take the choice, sorry if it's a bit small, the choice between the non-deterministic choice between two programs, and then compose it with V, it's like composing the first one or a choice composing the second one, and this is not exactly equivalence. So yeah, and these operators preserve roundness. So basically, if you round the operands, you get a rounded result. They also preserve feasibility. And now we get to actual programming language constructs. We could go directly with these, but it's nicer to have a very small set, exactly 3 basic constructs, and then define various programming languages on the basis of this. So here we have variants of the conditional. The first one is the extra guarded command, which essentially is a union, a choice between the various branches, each of which has a restriction. Then you have the standard if then else, and a variant which is the then only. And again, we can prove their properties. We don't have to postulate anything. So again, to take one at random, if we restrict to D the conditional, the Dijkstra conditional, it's like restricting every branch. Basically, it's what it says. Then next we come to loops. So here there's a whole set of notations, because loops have a number of variants. We start with the 0 repetition, p to the power 0, so that's essentially skip. Then fixed repetition, which is, for those of you who remember Fortran, this is the for loop or do loop of Fortran from 1 to n, so repeat exactly n times. Then we have the infinite loop, as in an a continuously running program, which is the infinite union, the infinite choice. Then we have the standard loops. Here I'm using the Eiffel syntax from A until C loop B. The last one are more the Pascal-like, or so with different syntactical conventions, C-like loops, the while loop and the repeat loop. They're all kind of the same. They differ by the convention of whether we use a continuation condition or an exit condition, thing like this. So they are essentially the power operator. We just compose a loop body with itself a certain number of times with some nice theorems. Like, for example, this one, which says, so we take the from loop, so A is the initialization until C, so this is the exit condition, and B is the body. So this says that if you take the range of such a program, that is to say the set of resulting states, well, it satisfies the exit condition, okay, as we would expect, but it's nice to be able to do this. And soon we're going to see that it also satisfies the invariant of the loop. So what is an invariant? We said this is not yet a loop invariant, it's a program invariant in general. We said that a condition is an invariant of a program if the range, remember that overline is the range of the post condition applied to the intersection of the invariant and the precondition is a subset of the invariant. So I'm using this notation here if I have a relation R, then R of C, if C is a subset, sorry, if C is a subset of the set of states, this is R of C is just the image of, okay? So you can see that if I take the image by post of the invariant, but we don't need to take all of the invariant. We only care about the invariant for states that satisfy the precondition. Then it's the range of that is a subset of I. So we have again a whole set of properties that can be proved from this. So for example, the post condition range and the range of P are both invariants of P. If I and J are invariants of P, then so are the union in intersection and so on. So altogether, we have several hundred such properties that have been mechanically proved. Not all of them are fascinating, of course, but it's really nice to have an extensive set of things that we know are true with the benefit of verification by Isabel. Yeah.
Not sure. On the top there, so the precondition is not the same as the loop condition.
So this is not for a loop. This is in general. It's an invariant of a program. So the invariant of a loop is actually defined next. It's a special case of, but this is an invariant of any program. It doesn't have to be a loop. So indeed, a loop invariant, now this is, I guess, the answer to your question, a loop invariant of a loop expressed in this form is a subset of the range of the post condition, so of the resulting space set, that is an invariant of the body, basically, but this basically says it has to be ensured by the initialization, and this traditional notion of loop invariant, right? But then it's an invariant of the body, but actually doesn't need to be an invariant of the body in general. It only needs to be invariant if the exit condition is not satisfied. Okay? So that's the relationship between the general notion of invariant and the specific notion of loop invariant. And then we have the fundamental loop theorem, which is that if I is a loop invariant and C is the exit condition, then the final state of the loop satisfies the exit condition and satisfies the invariant. And that's what we have, why we have loop invariance in the first place. Okay, then as you might have guessed, the notion of contract comes in. So we want to have a notation which really surprisingly is the Eiffel notation. I wonder why. Which is essentially saying, so if we write this, it means that Q is an implementation of phi. Okay? And we write it the way we would write it in Eiffel with a precondition and a postcondition. So we require precondition of phi, do implementation, ensure postcondition of the specification. Okay? So that's the notion of contract, and we again have a whole set of interesting properties, interesting or not, actually some more interesting than others. But for example, we also define the notion of weakest precondition a la Dijkstra, so the precondition of P with respect to true is the precondition of P and so on. But I'm rushing a little bit because I want to cover concurrency and then that will be it. The next thing that we have done is to say, I mean, obviously what I've seen so far could be dismissed as being the easy part of programming, right? And now what's really interesting is to start to handle the more tricky parts, and we've done only a bit of that, but one bit that we've started to explore is concurrency. So there's a first notion of concurrency, which is not really the one we want, but it's a starting point. It's what we call atomic concurrency. So if we take two programs, P and Q, the atomic concurrency is simply the program that could either execute P then Q or the other way around. And it has some nice properties. So again, a general approach in this work is really proof-driven, right? And mechanical proof-driven. So we define something and then we immediately try to find out what the properties are. I think much more in the style of what mathematicians typically do than what often computer scientists or people doing program semantics do. So of course, this is not good enough, and we take as example our beloved shared coffee machine, which is not unique to us. You've seen this model before. It's a rather limited amount of concurrency, but still we can have a deep technical discussion, or as the case may be, a shallow technical discussion, while both enjoying the preparation of our respective coffees. And Reto and I have very different tastes regarding coffee, so this is really critical. And there could be some various interleavings, right? If the basic operations are put capsule right, put capsule left, push the button on the left or on the right, then get the coffee. This is actually very much the kind of example that CSP people use, but we're on the other side of the channel. So they use tea, we use coffee. This is our major scientific contribution to the advancement of the science of concurrency. So anyway, this is the kind of concurrency that we really want to model. Why not just do P then Q, or do Q then P, but in fact interleave P and Q. And so how is this modeled? The general idea is that we need to be a bit more specific about the set of programs that we can manipulate. You can see that until now, I've been very vague about the details of the program. In particular, I've said absolutely nothing about the state, the set of states, S. It could be anything, and I think this is one of the good points of this approach, is that we can separate the stuff that is completely general, that could apply to imperative programming, object-oriented programming, functional programming, I think we can still use the notion of state in functional programming, and then the stuff that is really specific to a particular model. I think the error of people like Gilles Kahn and much of the traditional denotational semantics work is to introduce far too early notions such as binding, which are very specific to the kind of low-level computation that we are doing. So here, of course, we are going to have the equivalent of bindings at some point, but much later, and we don't need them to define things like loops, conditionals, and even recursion, and so on. So now we're still at a very high level of abstraction regarding the state. I'm not going to say anything about the state in this presentation, but we still need to say something about the set of programs. So we are going to limit ourselves to programs that are built in the following way, using the three fundamental operations. So we start from a set of basic programs, and it can be anything. It's just the atomic programs of our programming universe. And okay, 5 minutes is what I need. So then we are going to allow ourselves to apply the three fundamental operations. So this is a definition by structural induction, to be pompous. We can have a choice between two basic programs, or recursively through two programs built in this way. We can have a composition, or we can have a restriction. So this is the only way to go beyond this atomic concurrency definition, because if we don't know anything about P and Q, then we cannot, it doesn't mean anything to say we are going to interleave P and Q. So in order to be able to interleave P and Q, we need to know what elements P and Q are made of. That's why we need another assumption beyond what we have had so far, which is that P and Q are built as choices, compositions, and restrictions of things that are more elementary. And here, then we can define interleaving concurrency, and basically it's a case-by-case analysis, but to take just one case, then the real concurrent operator, which is going to be this one, says that if you have a choice, if P is a choice, then P is this correct? Yeah. Let me take the last one because I'm running out of time and I'm not so sure anymore. If both P and Q are basic, then we take atomic concurrency. Did I do it? And is this correct, or am I missing a P and a Q?
Probably not important.
It's probably not important at this point. Yeah. So it's probably correct, but I don't see it anymore. So then we at some point it is correct because we have proved things. So there is a whole set of laws in with respect to this concurrency operator, and partly what we wanted to do at this stage of the work, what we wanted to do was to take Hoare's laws, you know, the one that with all the grandeur of a British lord he brings to the world, like Moses coming down from Mount Sinai. We don't want them to be laws imposed by Moses. We want them to be theorems. And basically that's what we have achieved. So some of these laws actually correspond, some of these theorems actually correspond to the laws that were postulated by Hoare and his colleagues. And we don't want to postulate anything. We want to come up with definitions and then prove things, which is the purpose of this work. So that's what I wanted to present. The thesis was that, and still is, because I don't claim to have proved it yet, especially this word here, the entirety, this is the goal, right? I'm not saying it's what we have achieved so far. We want to be able to understand the entirety of programming in terms of elementary set theoretical concepts. And what comes next? Well, a lot. We need to model all programming mechanisms, including the hard stuff, various forms of concurrency, interrupts, exceptions, things like this. Also the advanced features of functional programming language. So we have our work cut out for us. We want to model actual programming languages. Actually, this is a little bit the old thinking. We want to construct. As I said, I want to reconstruct IFO completely from scratch, completely from sixth grade set theoretical concepts. We want to see if it's possible to teach programming this way. So we've started writing a book which explains the approach from the ground up, kind of pretending that the student doesn't know programming, but maybe he knows a little bit of mathematics. Again, 15-year-old level mathematics. This can also be implemented, and it would provide for potentially a very nice platform to play with programming language mechanisms and automatically, assume that you're devising your DSL, the domain-specific language, or you're trying to propose a new mechanism for Java or whatever. You could have this kind of workshop where you play around with programming language features, and if you are able to define them in a set theoretical way in this style, then you immediately get for free an interpreter, maybe a compiler, and a prover. You can actually, so I call it FLIP, maybe the name will change, but it's something that we've been thinking about. We have not done it, and we could also use this as the root of a new proof system. This is the kind of thing that Reto is looking at, and I hope it's a good opportunity to wish Yuri, 22 years later, a very happy birthday.